Hello, my name is Judea Hudson. Welcome to Lab 2, Motion of a Falling Object. Intro. Purpose of this lab will be to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. This lab will depict the effect of gravity and drag on an object. Our initial conditions. Our crumpled ball of paper initial position is 0, which is its point of rest. The vector position is only in the y direction because we are only measuring what happens to the ball as it falls on the y-axis. Here's some fundamental equations that we'll be using during our experiment. So that we could properly complete the computational model, Newton's second law showed that the net force of our object was equivalent to the change in the object's momentum and change in time, which is shown right here, F net, change in momentum and change in time. Then we can also derive from Newton's second law that the velocity update formula, which is tangential to the position update, formula. So here we have our velocity update formula, and then up here we have our position update formula. We'll also be using force of gravity and drag equations for our experiment. Now, the experiment details. We're going to crumple a piece of paper into a ball. Gravity and drag are our surroundings / forces acting on the ball. We're going to use Tracker to record our observations, and we're going to have two glow square models, one with drag and one without drag. Our initial position and velocity are 0, 0, 0. We're going to have some assumptions as well. The paper started at exactly 0 on the y-axis. The paper had an initial velocity of 0, 0, 0. Gravity and drag are the only forces acting upon our system. Here's a video of Tracker. Cool. Here we can see the ball falling down. Here we have the data from the ball, and here's what it looks like on a graph. Here is on our own graph made in Excel, and this is the information put into Excel to make the chart. Now, here's the computational model with no force. Here we have our initial positions. We have 0, 0, the mass of the ball being 0.013, and then we have delta t being 0.043. We have magnitude of acceleration due to gravity near Earth's surface, which is better known just like the constant force of gravity, 9.8, truly negative 9.8, but we put that in our math later. Then we have j hat, which is the unit vector for the position of the y-axis right here, pointing up. And then we have b equals 0 because we're not going to be doing any math with drag, so b can stay at 0. Now we have our loop right here, f net, and we have fg. Force of gravity is just mass times the mass of our object times gravity, which will give us our force of gravity. And then we have that for our ball's velocity. We do the math here, and we do the position math so that we can later get this video. Cool, and this is without drag. Now we have it with drag, same initial conditions, and then we have here, we have to get the speed of our ball, the force of gravity, and the force of drag, which we've now updated b to be 0.7, and then once that is all combined, we get our net force. And here is what that looks like here. Now, all data comparison. The model of drag right here resembles the tracker model, with the model without drag but the model without drag is substantially contrasts the tracker. As we can see, without drag, it seems as if the object keeps going further, even though it doesn't, because drag is what stops it, but this one does not consider drag. So here is the tracker, and here is the one without drag. Moving forward, the data most likely has a small margin of human error due to slight improper tracking of the object when clicking to track the ball. What does it mean? Terminal velocity. Terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down. Relating back to our object, this indicates that an object traveling at its terminal velocity experiences no net force. With that being said, drag is a crucial part of our net force because without drag, we would not be able to reach terminal velocity. Now, what if? Imagine the object was initially thrown downward. Would the terminal velocity of this case be the same or different from the case where the same object was initially dropped from rest? Regardless of the initial velocity, the final velocity will remain the same. This is due to drag and weight being the only significant factors within our experiment. Moreover, the object would just be slowed down until it reached the final velocity given to us in the computational model with drag. Thank you for your time.